Hi, I'm Willy, and I'm going to talk about the construction of oblivious transfer from LWE. So what we're interested in this work is oblivious transfer, which involves two parties, a sender and a receiver. And the sender has two messages, M0 and M1, and the receiver has some trace bit B. And the goal is, in the end of the protocol, for the receiver to receive the message MB. So to do so, they will interact using some oblivious transfer protocol. And then in the end, given this protocol, the receiver should be able to derive the message MB. So we would want this protocol to be secure. So what we'll ensure is that if a honest sender is interacting with a malicious receiver, then one of the messages that doesn't correspond to the receiver's trace bit should be hidden. From the perspective of a honest receiver, interacting with a sender should not reveal anything about the trace bit B that you showed. So for this work, what we'll be concerned with is a true message version of OT, where the whole protocol consists solely on one message from the receiver to the sender and a response from the sender to the receiver. So as to why people would care about this primitive, it turns out that it is very fundamental for multi-party computation, and there's several old results that show that this oblivious transfer is kind of MPC complete. And it turns out that more than just theoretical completeness, this is actually a primitive that is used in practice. And so let me dig a tiny bit more into details as to what flavors of security we're interested in. So what I gave just before was just a rough intuition of what one might require from an OT, but there are actually several flavors of it. So first, we might consider whether we provide security against parties who, adversaries who still follow the specifications of the protocol. That would be semi-honest adversaries, or full-blown malicious adversaries that can just behave arbitrarily. So in this work, we'll consider malicious adversaries. In that case, then comes the question of how we model security. And there's essentially two main ways of modeling security, either using game-based definitions or simulation-based definitions. Here, like I'll roughly talk about I'm referring to the universal compatibility framework. So each of them have advantages. So the main advantage of game-based definition is that it can work in the plain model, but the main drawback is that it's not composable. So even if the primitive is secure as a standalone, it's not clear that security still holds if used within a larger protocol. And for simulation-based security, it provides stronger security guarantees that are actually composable. But this is at the cost, at least for the true round version, true message that I just described, that requires the use of a trusted setup. So throughout this work, we'll be concerned with simulation-based definitions. And the setup we'll consider is the availability of a common reference string in the sky for both parties that has been generated in a trusted manner. A last distinction to make is whether security should hold when the adversaries are computationally unbounded. So if only ensure security when the receivers are computationally bounded, we say that the security is computational, and otherwise that it is statistical or information theoretic. So in the case of oblivious transfer, we cannot hope for a scheme that is information theoretic secure for both sides. But we can still hope for to provide this for at least one party. So in this work, we'll mostly focus on getting the best we can hope for in that settings, in those strong security notions. So here's a quick recap on what I think are the most notable works in constructing true message OT. It turns out that there's not that many constructions. And in terms of simulation-based security, there's only actually very, very few works. That's the lower part of this table. And in particular, there's particularly few constructions from LWE. So in particular, what we'll be concerned with in this work is this work by Piker, Nathanathan, and Waters that has the most green cases, so that's good. So we'll try to look at that. Yeah, so what do they achieve in this PVW paper? They show how to build a simulation secure OT that has some dual mode security property. So what does that mean? It means that there's actually different ways to set up the CRS, but the rest of the protocol remains the same. And depending on how the CRS was sampled, the security guarantees are different. So there's a first mode here in orange, where the CRS is sampled according to some orange distribution, where which ensures statistical security for the sender. And there's a second mode that ensures statistical security for the receiver. And of course, those two modes ensure computational security for the other side. That's actually an oblivious transfer protocol. So more than that, PVW actually proposed a very, very nice blueprint to build this kind of OT. And this blueprint is actually very modular, and they actually manage to give constructions from different assumptions. So DDHQR and LWE. And one particularly nice feature about those constructions is that they are somewhat efficient. They are not unreasonably efficient, and they're still like potentially implementable. So that looks very, very cool. So what's the problem? So my abstract take on this is that PVW is like well rounded, very strong, very nice. But if you look at it very closely and look at the LWE realization of this blueprint, there's a very small thorn, and that's very annoying. Like it's not as round as one could expect, but this is still very minor. So what was this thorn? Well, it turns out that PVW does not exactly show how to realize a full blueprint from LWE. In particular, it only realizes a weak version of the blueprint, and that results in some drawbacks. So in particular, the security of the receiver in the PVW construction from LWE is only computational, regardless of the mode, and the CRS can only be used once for security. So as long as you use the CRS in two different protocols, then for security, kind of all bets are off. And the very strange thing about this is that we do not really have, we don't have those problems at all in the constructions from DDHQR. So that's what we're doing in this paper. We're kind of removing, or at least smoothing that thorn. And we show how to actually build this kind of nice dual mode simulation security from LWE, with, to be more precise, with sub-exponential modulus true-noise ratio. So in particular, the OT we get can be instantiated in a statistical secure way. And as far as I know, that's the first statistical secure OT that achieves the above. And the CRS is also reusable. So that removes the main true problems of the PVW instantiation from LWE. But this is at the cost of using a slightly stronger assumption, like a slightly stronger flavor of LWE. Pretty much. So our roadmap for this talk will be to first discuss a bit the blueprint of PVW and how that's related to oblivious transfer, the strong notion of oblivious transfer, and then we'll show how they build that from LWE and how we fix it. So the blueprint of PVW is to use a very particular form of encryption to realize the oblivious transfer protocol. So in particular, the main idea will be to have the receiver generate true public keys and send them to the sender, while only knowing one associated secret key. So after that, the sender can encrypt both of her messages under each of the respective keys, and using the single secret key that he knows, the receiver can derive the message ID. So of course, here we are dealing with malicious adversaries. So a malicious receiver could generate just PK0 and PK1 with their respective secret keys. So that won't work as is. And the main idea, pretty much, of PVW, so if I want to sum that up in one sentence, is to tie those public keys together using the CRS. In a way, in particular, that the receiver will not be able to come up with those true public keys with true secret keys. So there will be, again, two modes of the CRS. Here, the orange one will provide statistical security for the sender. And what it ensures is intuitively that the receiver shouldn't get information about both the messages. So to be more precise, we want a strong definition of simulation security. And in some sense, what we want is that for all potential first message of the receiver, there should be at least one secret key that the receiver knows, in some sense. So the way we model that is by requiring the existence of an extractor that takes as input the first message of the receiver and extracts a bit B star such that the receiver cannot get any information about encryptions on the other 1 minus B star. So that's how we model security. And in the other mode that will provide security, statistical security for the receiver, what we want intuitively is that the first message that's sent by the receiver shouldn't reveal information about B. But again, we want something slightly stronger for simulation security. In some sense, we want to be able to extract both of the messages sent by a malicious sender. So what we'll do is that we'll require the existence of a simulator that produces a fake first message along with true secret keys. In particular, the indistinguishability in the bottom requires that those fake public keys that are produced by the simulator should look statistically close to the messages of the honest receiver. In particular, this intuitively implies that that the first message doesn't reveal any information about what secret key the receiver has. And to tie everything together, the last property that we require from this encryption scheme is some mode indistinguishability, which requires that the orange CRS and the green CRS are indistinguishable. So now that actually allows to argue computational security on the other side. So for instance, if we want to argue computational receiver security in messy mode, we'll simply switch the CRS from messy to decryption. And in decryption mode, we have statistical security for the receiver. And so overall, we have computational security for the receiver in messy mode. And similarly for the decryption mode. So that's the blueprint. And so the question now is, how do we realize this blueprint? And the main idea from PVW, their construction from LWE relies on a variant of the RegF encryption scheme, which looks as follows. So we'll be working over ZQ for some well-chosen queue, and the public key will be an LWE sample, so a noisy version of combinations of the rows of A. In order to encrypt, we'll do as follows. We'll pick a small vector of a small vector R and multiply on the right both A and the public key, and then kind of encode the message. So that's in a nutshell how what the RegF encryption is, but I still have to describe how like this construction should tie the public keys together. And we'll use a very simple correlation. We'll simply set that the difference of the public keys should correspond to the series. So the series will be a vector, an offset vector, that determines the difference between the two public keys that the receiver sends. Okay, so how does that make us closer from realizing a dual mode encryption scheme? So for sender security, here the series will be orange, and the main observation is that if you take the space of valid public keys, not necessarily like produced by the key generation algorithm, then actually most of them are message-lossy or messy, in the sense that if you encrypt a message M under C, the public C, then this is pretty much garbage. So what we'll do is to set the CRS to be a uniform offset vector, and we can argue that with good probability over the CRS, then at least, like for all choices of PK0, at least PK0 or PK1 will have this property. In particular, because there's a way to test whether such a public key is messy with a trapdoor for the matrix A here, using lattice trapdoor techniques, that gives simulation security. Yeah, so what about decryption mode? And again, here the goal is to produce a pair of public keys with respective secret keys. And a quite naive idea, but actually pretty elegant, is to set the CRS as a difference of two public keys. And because of the shape of the LWE assumption, that actually ensures indistinguishability of the modes. So the difference of true LWE samples will look uniform. So that's good. And then if you set the series this way, then you have a way here to set up both public keys while knowing both secret keys by outputting, well, PK0 star and PK1 star. But there's several problems. First, the simulator can only output one single pair of PK0 star and PK1 star because they are like kind of hard-coded in CRS. And the second problem is that the keys that the simulator produces are actually not completely fresh. So the reason is CRS, so that the CRS is computed as a difference of true public keys, so true LWE samples, and there's actually some correlation between the noise in the CRS and the noise that is used in the public keys. So the public keys do not look completely fresh given the CRS. And actually, those problems make that the CRS is the first problem implies that the CRS is not reusable. The second problem gives that we only know how to argue computational security in that context. So how do we fix that? Those were the two issues that we're trying to solve. Essentially, the main problem is that there's some correlation between the noise in the CRS and the noise in the keys, the keys produced by the simulator. And there's actually a pretty standard fix in the lattice, using lattice techniques, that kind of drown those correlations using something that's called noise flooding. And the way we'll achieve that is to require the noise in the public key to be much larger than the noise of an LWE sample defined by the CRS. So now, instead of being the difference of two LWE samples, the CRS will just be a fresh LWE sample, but with very, very small noise. And then we actually get rid of the problem if this E is much, much larger than E star. It also fixes the problem of being able to sample only one key, because now for any public key, you can define the trapdoored second key using S star. So that actually solves both of the problems for pretty easily. The only cost seems to be that we have to use noise flooding. So in order to do that, the queue that we are working on, so everything is in the queue, and the queue has to be sub-exponentially large. So we make use of a stronger assumption. Okay, so are we done? And there's a very annoying thing that we are actually not done, and that's because of something that I swept under the rug earlier. And the problem is actually now in the messy mode. So I claim that now that if we use noise flooding, we actually broke security in messy mode. And where I lied was when I said that we can test whether a public key was messy using an appropriate trapdoor for the matrix A. But it turns out that this test is actually linear in the modulus Q that we are using. So in particular, if we're using a sub-exponential modulus Q, now the extractor that we get is now not efficient anymore. So I should fix that. And the main idea will be to have kind of a more efficient messiness test. And to do so, we'll actually try to get a more efficient messiness property. So actually, I do not know how to get a better messiness test for a GEF, but what we use for decryption, for security in decryption mode, is kind of only the shape of public keys and secret keys. I actually didn't use anything about the encryption scheme. So what we'll do is to try to find another way to encrypt that has a better messiness test. And our main goal for that will be to use a randomized rounding function with the following property. So that has been introduced in a prior work. With the following property, if C looks pretty much like a good public key, then we have this indistinguishability, so this approximate equality rather. And what does it mean? Recall that in the real RegF encryption, the masking factor was R times C. So here what we're saying is that this masking factor can be recovered using R times A and the secret S. So that's kind of a correctness property. The second property that this randomized rounding achieves is that this rounding is actually uniform if C is not a valid kind of a valid public key in some sense. So that gives a somewhat natural way to set up our encryption scheme. And now we'll replace the mask by a rounded version of this mask. So now what it gives is that if as long as property true holds, as long as we're in this regime, then the public key C is messy, right? The property here. So the mask looks uniform, and so mask completely the message. So I didn't write that, but the indistinguishability here is set to 0. And it turns out that this property is actually a simpler messiness property than what has been used in prior work. So in particular, this, using lattice trapdoor techniques, we can test in time essentially independent of the modulus Q. So that's pretty much our construction. So I lied a tiny bit. So here the approximate, the correctness here is only approximate, so we have to amplify correctness somehow. So we lose a bit in efficiency here. But overall, what we give is a new dual mode encryption from a construction of dual mode encryption from LWE, albeit with sub-exponential modulus ratio, and that gives that directly gives a dual mode OT that can achieve statistical receiver security if set in the appropriate mode. And as far as I know, that's the first scheme that achieves that, and where the CRS is reusable. But again, this is at the cost of using a larger queue, so this is slightly less efficient, and we have to rely on a stronger assumption. And the main tool that we use is a variant of the reggae function where the public keys are the same, and the secret keys are the same, but that has a nicer messiness property. So it's easier to test whether public key that has not been necessarily produced by the keygen algorithm statically hides the underlying messages. And for natural open questions, a natural open question is to remove this restriction in red and have a construction from polynomial modulus. And something that I'm actually a bit curious about is if there are other applications of the rounding functions. I think the rounding function has really nice properties, and I would be interested in having more applications of that. Yeah, that's all for my talk. Thank you for your attention.